Hi everyone. In this lesson we're going to go over Taylor series. Now a Taylor series is a method by which we can take a function f of x and express it as a series or sum of polynomials. Now there are all types of reasons why we would want to do this. In particular, notice that polynomials are very easy to evaluate. So if you're given a function like this, which is a second degree polynomial, if you want to evaluate f of 2 or f of 3, that's very easy. All you're doing is using the operations of addition, subtraction, multiplication, and division, and then you can evaluate the polynomial at any point. So if you're given a function like the sine of x, how could we evaluate the sine of, say, 2 or 3? Or the cosine of 2 or 3, or the tangent, or the natural logarithm. All right, how do we evaluate those? Well, if we can express them as a Taylor series, which would be a sum of polynomials, then those polynomials would be very easy to evaluate, and we could approximate the sine of 2 or 3 with our Taylor series approximation. So that's one reason why the study of Taylor series is so important. So to develop how we can take a function f of x and express it as a sum of polynomials, let's start with this. So suppose that we're given a function f of x, which is continuous at some base point a. So a is going to be a fixed value that's given to you. And also let's suppose that the nth derivative of f of x exists at x equals a as well. Now let's notice this to start. If we consider the polynomial of degree 0, which is a constant function, p0 of x equals f of a, then this is going to be the best constant function or 0-degree polynomial that approximates f of x at a, f of a at that point. For example, consider this illustration we have here. So you notice that this is our function f of x here. And we want to approximate f of x at that point with the best constant function. Well, this point right here on the y-axis, that point right there is f of a. And this dashed line right here is the function y equals f of a. And so clearly that's going to be the best possible constant function that approximates f of x, which is the graph right here, near the point x equals a, right? This would be your best 0-degree polynomial or constant function that approximates our function f of x right here, okay? If we drew a constant function down here, well, obviously that's not going to be the best approximation at this point because f of a is all the way up here. Now, suppose we want to find the best first-degree polynomial approximation to f of x. Okay, so what we're going to do is this next. So what we're going to do is we're going to assume that our first-degree polynomial approximation, call it p1 of x, is going to take this form. So it's going to be f of a plus some constant, call it c1, we have to figure out what that is, times x minus a. Now what we need to do is figure out what should this c1 equal. Well, it's pretty clear that what we need for this function is we need p1 of a to equal f of a. Well, that already happens. Notice if we put a in here for x, this term goes to 0 and we get f of a. So this already holds. Now we also want the derivative p1 prime at a to equal f prime of a. All right, so that's what we have right here. Now if we take the derivative of this function, notice that the derivative of this function, p1 prime, of x. If we differentiate this, well, that's just a constant, so its derivative just goes to 0. And the derivative of this right here, well, notice that that's c1 times x minus c1 times a. Well, the derivative of this is just going to be c1. Okay, so for this to hold, then we need c1 to equal f prime of a. So here we go. Right there is our best first degree polynomial approximation at x equaling a. Notice that this is a first degree polynomial approximation because it's x to the first power right here. Okay, now also notice that for this function, the way we have it written, right, keep in mind the a is a constant, f of a is a constant, f prime of a is a constant. Notice for this function, we do indeed have that p1 of a equals f of a. That does indeed hold, because if we put a in for x, this goes to 0 and we're left with f of a. Also notice that p1 prime of x, if we differentiate this, we're going to be left with just this number right here. So it's f prime of a. And of course, if I put a in here for the x, we get p1 prime of a equals f prime of a. So there you go. Those first two conditions now hold. All right, and if you were to graph this function, here's a typical graph of what it looks like down here. Right here is the graph of what this function would look like. Notice that p1 of a equals f of a. F of a is right there. And also notice that the slope of this dashed line, which is this function right here, is the same as the slope of your function f at x equaling a, because notice the dashed line is tangent to the graph at x equaling a. Okay, so here is our best first degree polynomial approximation. Take note how that looks. Now let's find the best second degree polynomial approximation. Okay, so to find the best second degree polynomial approximation, we take p1, right here it is, this is p1, and we add to it a second order term, call it c2, we have to figure out what the c2 is, times x minus a squared. Okay, now what we require now is that the second derivative of p2 at a equal the second derivative of f at a. Okay, now if we take this function right here and we differentiate it 2 times, notice that the first part right here, that is a first degree polynomial. If you take its derivative twice, this is just going to go to 0. Now, what is the second derivative of this part right here? Well, the second derivative of that is going to be 2c2. Here's the first derivative. That's the first derivative of this part. Then the second derivative is going to be 2c2. Okay, so this is actually p2 double prime. And so we set this equal to the second derivative of f at a, and we obtain that c2 should be f double prime of a divided by 2. Okay, so right here is what we end up with for p2. Notice that this part right here is p1, and then we have this second part that we just determined right here. Now this function, right down here we have a graphical representation of a typical p2 curve. Right here you'll notice that it's a quadratic, so it has some curvature to it right at x equaling a. Okay, and it is designed so that p2 of a equals f of a, and p2 prime of a equals f prime of a, and p2 double prime of a equals f double prime of a. it's easy to see that all of these hold for this particular function. Okay, now what we want to do is create a third degree polynomial, call it P3, in which all of these conditions are going to hold for P3, and P3 triple prime of A equals F triple prime of A. So that's what we want to do next. Okay, so let's scroll down here and see how we do that. Okay, so to find the best fitting third degree polynomial, what we do is this. Notice that this part right here is P2. That's P2. And now we add on another term. This is going to be a third degree polynomial right here called C3 times x minus a cubed. Now what we have to do is figure out what the C3 should be, so that in addition to all the other conditions, we also have that, and that should be a 3 right here, P3 triple prime of A equals F triple prime of A. So we need this to hold. All right, well, if we take the third derivative of this function that we have written right here, if we take the third derivative, notice that the third derivative of this part right here will just be 0. Okay, because it's a second degree polynomial. If you take 3 derivatives of it, you will eventually get to 0. The third derivative of this part, well, let's see, what's that going to be? Well, the first derivative is going to be 3c3 times x minus a squared. That's the first derivative. The second derivative is going to be 3 times 2 times c3 times x minus a. That's the second derivative. Then the third derivative is just going to be 3 times 2 times c3, and that's it. It's just going to be a constant, or 3 factorial times c3. This is the third derivative of this function up here. So now what we do is we set the third derivative of P3 at A equal to F triple prime of A. Well, this is the third derivative right here. So setting this equal to F triple prime of A, divide the 3 factorial under, and we get C3 equals F triple prime of A over 3 factorial. And there you go. Here is our best fitting third degree polynomial. Right there it is. Now let's just take note at this point of something. Let's notice if we look at P3 of A, what do we get back? Well, if I put A in for all the x's, notice this goes to 0, 0, 0, we get f of A back. What about the first derivative of P3 evaluated at A? Okay, well, if we take the first derivative of this function right here, the first derivative, P3 prime, that's going to be, okay, the derivative of this is 0. Derivative of this is f prime of A. Derivative of this part is going to be f double prime of A times x minus A. And the first derivative of this piece is going to be, put it down here, f triple prime of A over 2. We drop the 3 down. That's going to cancel with one of the 3's here, times x minus A squared. Now, if we evaluate P3 prime of A, that we have right here, notice if we put A in for the x here and the x here, these go to 0. You're left with f prime of A, which is exactly what we want. Also, if we evaluate P3 double prime of A, okay, now here is the first derivative. So if I take the second derivative, notice that P3 double prime of x in general, The derivative of this is going to be 0. The derivative of this piece is going to be f double prime of a. And then the derivative of this part right here, we drop the 2 down, we're going to get f double prime of a times x minus a. Well, notice if we put a in for the x's here, this goes to 0, and we get f double prime of a, which is exactly what we want. And then as for the third derivative, well, we see we designed P3 so that the third derivative does satisfy this right here. And so we have P3 triple prime of A does indeed equal F triple prime of A. Okay, so the important thing to remember here is that this polynomial right here is designed so that this holds, this holds, this holds, and this holds. And notice down here we have the graphic of a typical third degree polynomial approximation to a function right here. Okay? Notice how this graph fits the graph of f a little better near x equaling a than the previous graph did that we have up here for our second degree polynomial approximation. Notice that that was right here. Okay, so it's a little better fit, the third degree polynomial approximation down here. Notice that this is a little tighter fit, further away from a. Okay, now if we continue in this manner, what happens when we continue? Well, the next term we would have here, we can see a pattern now. The next term is going to be the fourth derivative of f at a divided by 4 factorial times x minus a to the fourth. And then the next term would be the fifth derivative of f evaluated at a over 5 factorial times x minus a to the 5th power. And we just keep going like that until we get to the desired degree of the polynomial that we want. Okay, so what we have is we have this formula down here now for the nth degree Taylor polynomial. So right here is our formula. Right here it is. You notice we have f of a, that's a constant, plus. Then we take the first derivative of f, evaluated at a, multiply by x minus a to the 1st power. Then we take the second derivative of f at a, divide by 2 factorial, or just 2, multiply by x minus a squared. Then, continuing, we have the third derivative of f at a, divide by 3 factorial times x minus a, and that should be a 3 right there, cubed. And then we just continue, and then we end with the nth derivative of f at a, divided by n factorial times x minus a to the nth power. This is called your nth degree Taylor polynomial, expanded about x equaling a, whatever the base point a is that you're working with. Now if the a is 0, sometimes you'll see the Taylor polynomial referred to with a special name. You'll hear it called a Mclaren polynomial. So sometimes you'll hear that referred to when the base point about which you're expanding is the origin, or a equaling 0. Let's take a look at an example down here. Now in this example, we want to find a 5th degree Taylor polynomial for the sine function expanded about 0. And then we want to find a general formula for the nth degree Taylor polynomial and write our answer using summation notation. Now, what we have to do here is we have to apply this formula that we have for the nth degree Taylor polynomial. Now, in this formula, all of these a's are 0. Just keep that in mind. All of these a's are actually 0 for this particular problem. And now what we have to do is looking at the coefficients, f of a, f prime of a, f double prime of a over 2 factorial, and so on. We want to write out these coefficients and try to identify a pattern. So we want to write out these coefficients for various values of n. So we're going to take the nth derivative of the sine function, evaluate it at 0, divide by n factorial as n varies from 0 to 1, 2, 3, 4, and so on. Write out these values and try to identify a pattern. So the easiest way to do that is to create a table like we have right here. So the first column just identifies the value of n that you're working with. The second column here we have listed is the nth derivative of the sine function. And then the third column, we take the nth derivative, evaluate it at a, which is 0 in this case, and divide by n factorial to get these numbers. And then we try to identify a pattern for these coefficients that go along with the x minus a terms. So notice that the first derivative of sine is cosine. Then the second derivative of sine, well, that would be the first derivative of the cosine, and derivative of cosine is negative sine. So here is the second derivative. You see that's when n is 2. Then the derivative of negative sine is going to be negative cosine. And so this is going to be the third derivative of the function we started with. Derivative of negative cosine is positive sine. And so this is the fourth derivative of the sine function. Okay. Then derivative of sine is positive cosine, and that would be the fifth derivative of the function we started with. So right away you can see a pattern already. You see that we have sine, cosine, negative cosine, then it starts over again. Sine, cosine, and it'll just keep repeating. Negative sine, negative cosine, and so on. Now we have to evaluate these values for various values of n. So we take the original function, put 0 in here for x. That's our value of a that we're using. And sine of 0 is 0. Okay, so that's what f of a is going to equal, this first term right here. So that's going to be a 0. Then when n is 1, we put 0 in here for that x. Cosine of 0 is 1 divided by 1 factorial, which is 1, of course, and we just get back 1. Okay, so this term right here is going to be 1. When n is 2, the second derivative of sine is negative sine of x, so we put 0 in here. That's the a. Sine of 0 is 0. Okay, and technically we would be dividing by 2 factorial here, but 0 divided by 2 factorial is just 0 again, of course. And so this term right here is going to be 0. When n is 3, we take 0, put it in here for that x. Negative cosine of 0, that's negative 1, and we divide by 3 factorial. And so this term right here is going to be negative 1 over 3 factorial. And instead of writing the 3 factorial as 6, it's sometimes easier just to leave the factorial in there. That will make it easier to identify a pattern. Then the next term, when n is 4, we put 0 into the fourth derivative of the sine function. That's just going to be 0. So technically this would be 0 over 4 factorial, but that's just going to be 0 again. And then when n is 5, we have the fifth derivative of sine is cosine. put 0 in here for x, cosine of 0 is 1, divide by 5 factorial, and there you go. That's going to be the coefficient when n is 5. Of course, 5 factorial is 120, but I recommend just leaving it as 5 factorial. And so what we have then is down here we have our 5th degree Taylor polynomial. Let's take a look at it. So here we have our 5th degree Taylor polynomial. Notice we have 0. This 0 is that one, plus 1 times x minus a to the first power. Keep in mind a is 0, so what we have right here is really x minus a to the first power. That's what that x is. And this 1 right here is that number. Then 0 times x minus a squared. That 0, this 0 right here is this one. Then minus x cubed over 3 factorial. Keep in mind we have a negative 1 over 3 factorial. That's coming from right here. Okay, so there's our negative 1 over 3 factorial times x minus a cubed. Plus 0. This 0 right here is this one, times x minus a to the 4th power. And then plus 1 over 5 factorial times x minus a to the 5th. And then we can simplify this a bit. Just drop out all the zeros. And right here is our 5th degree Taylor polynomial. And now you can see a very nice pattern from this. What would the 7th degree Taylor polynomial be? Well, P7 of x, all you would have to do is, we'll just put it right down here. If you wanted the 7th degree Taylor polynomial, it would just go minus x to the 7th over 7 factorial. See the pattern? Plus, minus, and you go by odd powers of x. Then the next term in your Taylor series expansion would be x to the 9th over 9 factorial, and then minus x to the 11th over 11 factorial. This would be P11 of x, or the 11th degree Taylor polynomial. Notice that you don't have any even powers of x. That's because of these zeros right here, here, here. Notice that all of these zeros correspond to when n is an even number. Okay, and so that's our 5th degree Taylor polynomial. Now here we have a graphic of how our Taylor polynomials look in comparison to the sine function. So notice that what we have here, this curve is the graph of our sine function. Okay, so that curve right there, that's our sine. And the dashed line, that's our 5th degree Taylor polynomial that we found. So that we have right over here. Okay, so recall that that is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Now take note that this is the point about which we expanded. That was the a, which was 0 on the x-axis. And notice how the graph does approximate the sine curve relatively well, close to 0. Now if you move away too far, notice how the graph does diverge away from the graph of the sine function eventually. Okay, so it's pretty accurate out to about here and here. And notice also you have a certain type of symmetry with respect to your approximation. Now let's take a look at the 7th degree Taylor polynomial. Remember, to get that, all we have to do is take our 5th degree Taylor polynomial and subtract x to the 7th over 7 factorial. And that's what we have right here. And let's see how that compares to the 5th degree Taylor polynomial approximation. So right there's our 7th. Let's take away the 5th. Okay, so there is our 7th degree Taylor series approximation for the sine. Notice that it is a little better approximation to the graph of sine, a little further away from the base point A. Okay, so once again, here's our 5th degree right there, 5th and 7th. Notice how the 7th is a little better approximation. Then to get the 9th degree Taylor polynomial approximation, we would just take our 7th and add on x to the 9th over 9 factorial. And that's what we have right here. And let's see how it compares. So right there it is. And you notice that it is a little better approximation further away from our base point A, about which we expanded, than either the 5th or the 7th degree Taylor polynomial approximation. So those are pretty good approximations, you can see, for a certain distance away from the base point about which you expanded. And then after a while they do diverge from the graph of the sine. And the higher the degree that you take, the better your polynomial approximation is further away from your base point A about which you expanded, in this case A being 0. And just also note that we didn't talk about the even degree Taylor polynomials for this approximation because notice that all of the coefficients that go with even powers of x are 0. So P6, the 6th degree Taylor polynomial approximation in this case, is just the same as P5 because the coefficient that goes with x to the 6th would just be 0. And the same for the 8th degree Taylor polynomial approximation in this case. P8 would be the same as P7 in this case. So that's why we didn't talk about the even degree Taylor polynomial approximations for the sine. All right, now let's find a general formula for the nth degree Taylor polynomial approximation for the sine function. So recall, for the sine function, we've derived this formula. So our general Taylor polynomial expansion for the sine function will be of the form x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And then we would end with x to an odd power, which we could write as 2n plus 1. And this is either going to be a plus or minus, you see, depending on the odd power that you end with. So we have a plus minus here, divided by 2n plus 1 factorial. And notice that you can write that like this down here. So, and this here should actually be a 2n plus 1 right there. That's the degree of this expansion. So we have the summation from k equaling 0 to n, negative 1 to the k. That will give you the plus minus pattern. X to the 2k plus 1 divided by 2k plus 1 factorial. So this is how you could write this polynomial right here using summation notation. Let's just notice that if you put 0 in here for k, negative 1 to the 0, that's going to be 1, times, if we put 0 in for the k up here, we get x to the 1 power over 1 factorial. Okay, so that's going to give you this x right here. Then if we put 1 in for the k, we get negative 1 to the 1, that's going to be negative. X to the 2 times 1 plus 1, that's going to be x cubed, divided by 2 times 1 plus 1 is 3 factorial. Okay, so you see how we get that term. Then if we put 2 in for k, we get negative 1 squared, so that's going to be plus x to the 2 times 2 plus 1, that's x to the 5th, over, and if we put 2 in here for that k, that'll be 5 factorial. And so you see how we get that term. And then one more. If k is equal to 3, negative 1 to the third is negative. 2 times 3 plus 1 is 7. X to the 7th over. And then, of course, we have 7 factorial there. And so you see we are recovering that term. And this goes all the way out until k is eventually n. And then you get either a plus or minus here, depending on whether this n is even or odd. So you get plus or minus x to the 2 times n plus 1 over 2n plus 1 factorial. So there you go. You see how this summation is generating this Taylor polynomial up here of degree 2n plus 1. And that completes this example. Now in this example, we would like to construct a 5th degree Taylor polynomial for the sine function again, but now we want it expanded about pi over 4 instead of 0 as in the previous example. So once again, to use our Taylor polynomial formula, we have to identify the coefficients that go along with the powers of x minus pi over 4 in this case. You see all of these a's in here are going to be pi over 4 now. And so we need to identify a pattern for these coefficients that go along with the powers of x minus pi over 4. Now to determine these coefficients, once again we construct a table like we did in the previous example. The first column are the n values that we're working with. The second column are the nth derivatives of our function we're working with, in this case the sine function. And the third column are the coefficient values. Those are the values of the nth derivative of f at pi over 4 divided by n factorial for various values of n. So to evaluate our first coefficient right here, we put pi over 4 in for this x, and we just get root 2 over 2. Notice the sign of pi over 4 is the square root of 2 divided by 2. Now keep in mind for this first value here, the n is 0, and 0 factorial by convention is 1. And so the denominator here is just going to be 1. So we just get root 2 over 2 for this when n is 0. Then when n is 1, we put pi over 4 in here for this x. Now the cosine of pi over 4 is also root 2 over 2. 1 factorial is just 1 again, and so we get just root 2 over 2 for our second coefficient. Then when n is 2, we put pi over 4 in for the negative sign of x. Now that's going to be negative root 2 over 2. And then we divide by n factorial, which is 2 factorial. And simplifying that, we get negative root 2 divided by 2 times 2 factorial. So that is our third coefficient, or our coefficient when n is 2. Then when n is 3, putting pi over 4 in for the third derivative of f, we get negative root 2 over 2 divided by 3 factorial. And this simplifies as negative root 2 over 2 times 3 factorial, just moving the 2 into the denominator there. When n is 4, we put pi over 4 in for this x into the fourth derivative of our function. We get root 2 over 2 divided by 4 factorial, which simplifies as root 2 over 2 times 4 factorial. And now we can see a pattern. The next one is going to be root 2 over 2 times 5 factorial. Okay, so these are the coefficients that go right up here in this formula. So once again, our first one here is root 2 over 2 Our second one here is root 2 over 2. This one, when n is 2, or our third coefficient, is negative root 2 over 2 times 2 factorial. The fourth one here, or when n is 3, that's going to be negative root 2 over 2 times 3 factorial. And so on. And let's take a look at our polynomial down here. So right here, this is P5, our fifth degree Taylor polynomial for the sine, expanded about pi over 4. Notice we have root 2 over 2 plus root 2 over 2 times x minus pi over 4, then minus root 2 over 2 times 2 factorial. Of course, this would be 4, x minus pi over 4 squared, minus root 2 over 2 times 3 factorial times x minus pi over 4 cubed, and then we have root 2 over 2 times 4 factorial times x minus pi over 4 to the fourth, and so on until we end with 5. All right, so there is P5. Now right down here we have a graph of what P5 looks like in comparison to the sine function. Notice that this point right there is pi over 4 on the x-axis. And that's the point about which we're forming our Taylor polynomial. Notice how the polynomial P5 does give a good approximation to the sine function in a small interval around pi over 4. So notice it does start diverging right around this point. And then if we go back to the left, it starts diverging around here. Okay, notice you sort of have a symmetry around pi over 4 as far as the distance of your divergence goes. Now if we wanted better accuracy, we could take out a few more terms here. And you can see the pattern. If we wanted to add more terms here, the next one would be minus root 2 over 2 times 6 factorial, x minus pi over 4 to the 6th, and then minus root 2 over 2 times 7 factorial times x minus pi over 4 to the 7th power, and then so on. The next one would be a plus. Okay, notice the pattern. Plus, plus, minus, minus, plus, plus, minus, minus, then it would be plus, plus again. Okay, and so that's how you form your Taylor polynomial for this problem.